Je vois pas ma mère, donc
Je vais aller jeter.
D'accord, on fait les rabats.
C'est bon.
Ouais, c'est pareil.
des animaux.
C'est pour ça que l'anus, ça fait l'anus. Allez-y, prenez place. Vous verrez, c'est extrêmement confortable. Vous allez entendre un programme extraordinaire.
Quelque part,
Merci Clément. Il manque une personne.
envoyer un ami. Je vais le chercher, je vais lui envoyer un message, je vais l'attendre. Un idée, donc ça c'est pas. Ok. Changement de température, ça s'est élevé.
On se laisse 2 minutes pour les tout derniers arrivants. Alors j'en profite, il y a un micro qui est au centre de la salle, c'est ça, bon micro, voilà. Et en fait, les personnes qui sont à distance entendent très très bien ce qu'entend ce micro qui est extrêmement sensible. Donc essayez de, si vous murmurez, ce qui peut arriver dans une assistance comme ça, essayez de ne pas le faire trop fort. Voilà. Voilà. Parce qu'en fait, le jury n'entendra que vous. Alors que vous pensez murmurer en toute confidentialité, ce sera exactement l'inverse. Très bien, je propose que nous commencions. Donc, bonjour à toutes et à tous, bonjour à Nour, bonjour aux membres du jury. Donc, nous sommes ici aujourd'hui réunis pour la soutenance de thèse de Nour Skaf, dont le titre de la thèse en anglais est Self-Optimization of Adaptive Optics and Characterization of Exoplanetary Systems. Bonjour, allez-y, prenez place. Nous allons commencer. Cette thèse sera soutenue devant le jury composé. Je vais commencer par les personnes les plus éloignées. Vanessa Bailey, qui est astronome au Jet Propulsion Laboratory de la NASA. Maud Langlois, qui est directrice de recherche au Centre de recherche astronomique de Lyon. Marcel Carbillet, qui est professeur d'université, l'Université de la Côte d'Azur, et astronome à l'Observatoire de la Côte d'Azur. Olivier Guillon, qui est professeur à l'Université d'Arizona, et aussi astronome au télescope Subaru. Pierre-Olivier Lagage, qui est directeur de recherche au CEA. Anthony Panetti, qui est chercheur CNRS Olesia, et Giovanna Tinetti, qui est professeur à University College London. Voilà, j'espère que j'ai oublié personne. Et donc moi-même, qui suis président de ce jury, et qui m'appelle Guy Perrin, et qui suis astronome à l'Observatoire de Paris. La thèse, la soutenance, va se dérouler en plusieurs étapes. La première étape, nous allons entendre un exposé de Nour pendant 45-50 minutes grand maximum. Ensuite viendra un temps de questions et d'échanges avec le jury. À la fin, je demanderai aux docteurs de l'assistance s'ils ont ou si elles ont des questions, aux docteurs, je précise bien. Et puis, le jury se retirera, délibérera. En fait, c'est vous qui allez vous retirer pendant que nous délibérerons. Donc, on vous priera de quitter la salle. Vous pourrez aller vous abriter dans le hall Uranie qui est juste à côté. Vous profitez des beaux jardins de l'Observatoire de Paris, à Bedon. Et puis, nous vous rappellerons, lorsque la délibération sera terminée, pour vous annoncer le résultat. Voilà, très bien. Écoute, Nour, donc 45 minutes. Cinquantaine maximum, nous t'écoutons. Et maintenant, je vais passer à l'anglais. La soutenance sera faite en anglais. So, we are now ready to start. Nour, the floor is yours for 45-50 minutes.
Thank you. Thank you to all of you for being here today. It's a pleasure for me to introduce my work over the last couple of years. Before I dive into the astronomy part of it, let me first give you some context about when I started my PhD, and of course it doesn't work. Here we go. Well, I started my PhD at the end of 2019, as you, I'm sure all of you remember, the famous year 2020 when started with the big bushfire in Australia that rose a lot of anxiety regarding climate change. And then the COVID-19 pandemic started, which really paralyzed the whole world. Then, as I moved into the United States, there were the biggest social movements of the history of the United States, with the Black Lives Matter movement. And all of this emphasized in some ways the world inequality gaps. And so literally the world was falling apart. And here I was starting my PhD. And so naturally some questions arose of, why do we keep doing astronomy when the world is falling apart? Why do we keep spending billions of dollars into wondering about our place in the universe and wondering if there is life out there? Well, if there is one main lesson that I'm gaining from this PhD work in astronomy is how everything is actually connected. And I hope you will see how astronomy can be a mirror to what is happening on Earth. All right, so during this presentation, I will first introduce the scientific context of the exoplanet world. I will then dive into the instrumentation section for how do we observe exoplanets, especially in direct imaging. Then the next section will be regarding on planet formation, and I will be especially focusing on the Beta Pictoris system. And my last part will be on atmospheric characterization, and then I will conclude to hopefully see how everything is connected together. All right, exoplanets. Well, since the beginning of, pretty much since the dawn of humanity, we have wondered about our place in the universe. And it's only about 30 years ago that the first exoplanet was discovered, and we could start to have some answers regarding our place in the universe. Since then, more than 5,000 exoplanets have been discovered with very different detection methods. And there is a huge diversity of exoplanets. And in fact, most of the planets that we have discovered in the universe, in our galaxy, are far different from the planets that we have in our solar system. And from what we already know, there is at least 4 times more planets than there are stars. So if we take only our galaxy, the Milky Way galaxy, which has approximately 200 billion stars, that means there is quite a lot of planets still to discover and to be able to understand. And here is a plot that shows the mass distribution of the planets that we have already detected. And as you see with the different detection method, and as you see, there is each method has different type of exoplanets. So there is really a big observational bias on what kind of exoplanet we can discover. And so the first part, so the blue stars that you see here on the top part represent the directly imaged planets. And so the work of my first part on instrumentation, the point is to be able to detect more planets closer in to their host star and with lower masses. And I will be then later discussing about the Doctor Who algorithm for that. The second part, we study this planet here on the left part. This is the Beta Pictoris D planet, and on the third part, we have the hot Jupiters, which I will discuss later on. So from all of that arises several questions. First, regarding the diversity. Where does the diversity of exoplanets come from? We see so many of them and so diverse, so far more diverse than we have in our solar system. And then naturally the diversity comes from the formation processes. How do they form? Because depending on different formation processes, we will have different type of planets. And then what is exoplanet population demographic? Because as we have seen in the previous plot, some planets are like mainly giant planets and some smaller ones. And we do not have a complete picture of the exoplanet population demographic. And out of all of these planets, of course, we wonder if some of them could be suitable for life. And so here is how everything is actually connected. These questions we need to answer. We will move forward to answer them, which of course I won't answer all of them right now. Anyway, but one of the key aspects to be able to answer these questions is to go through the direct imaging, which will play a key role in answering these questions. All right, so there will be three axes around my PhD. As I mentioned, there is the instrumentation development, and everything is interconnected. So with instrumentation development, we are able to have better images and better spectra that gives information on how planets form, which also gives better spectra for atmospheric characterization. And both of them are connected because from atmospheric characterization, we can trace back the formation history, and that validates and guides for the instrumentation development. And all of that is part of the big picture of paving the way for the next generation of big telescopes to image and characterize Earth-like planets. All right, now let's dive into the instrumentation for exoplanet imaging. Well, observing directly an exoplanet is actually extremely challenging, and one of the reasons for that is because the star brightness is far greater than the planet itself. So imagine for a second that you're in Hawaii and you're trying to observe a planet next to a lighthouse, which is in San Francisco, and which is like a tiny firefly next to the brightest lighthouse. And obviously, you would have despite the Earth's curvature, you would have a lot of challenges for that. And so the star brightness, and the other issue is the tiny separation between the planet and the star itself. And to overcome this issue, we have coronography, which comes and blocks the light of the star to be able to increase the contrast of the planet. And we need big telescopes because the resolution is linked with the diameter of the telescopes, and the bigger the telescope is, and the more we can go closer in separation. So just to give you an idea of what does it actually mean? So for a Sun-Earth system in visible light, we receive 10 billion photons from 10 billion photons from a star for one single photon from the planet. So there is really something like huge to overcome, and what we currently have right now is a contrast of 10 to the minus 6 at 0.5 per second, being the separation. All right, another big technical challenge to overcome is the Earth's atmosphere. In fact, when the light comes from the star, it's spherical, but then with the distance, it's the wavefront is flat. And then it comes to the Earth's atmosphere, where there is air and wind and things that come to impact the shape of the wavefront. So it's not something flat anymore, but it's something shaky. And when it comes to the telescope, it's not an accurate one, but it's a blur. And this blur is scientifically it's impossible to use it. So what we use to compensate for the Earth's atmosphere is adaptive optics. But as you can imagine, for an exoplanet that is really tiny next to its star, we need to have a really extreme precision over the Earth's Earth atmosphere correction. And for that, we use extreme adaptive optics also because it sounds pretty cool. All right. So regarding why is it such a problem, especially for imaging exoplanets? And well, the problem is that aberrations from the Earth induces what we call speckles on the scientific image. So here is a choreographic image of a multi-planet system, which is called HR8799. Yes, we love beautiful names. And as you see here, the speckles, they really mimic the exoplanet signal. So try to see speckles as basically planet identity theft. And the problem is that they have pretty much the same contrast, and the amplitude is a few dozens of nanometer. And again, there is a direct correlation between the speckles intensity and the aberration amplitude. So we really need to be able to very perfectly correct for the optical aberration to get rid of the speckles to better see the planet themselves. And why do we need extreme adaptive optics? Is here that shows the choreographic image of this multiplanetary system. On the left-hand side, you have just simple conventional adaptive optics. And on the right-hand side, you have extreme adaptive optics. So you see there is way less speckles, and you can even detect another planet. So now, how does it actually work? Well, the adaptive optic system, there is three main components to it. First, we need to understand what is the distortion made on the wavefront. So for that, we need to sense the wavefront, and we use what we call a wavefront sensor. And then we use a computer, a real-time control, that will transfer this information into action with the deformable mirrors that will take the exact opposite shape of the aberration to then send it flat, or almost flat, but life being life and never perfect, there is always what we call atmospheric residuals. And beyond the adaptive optics loop, there is, you see in this box here, there is what we call the non-command path. And these are optics that come to induce some aberrations in the scientific image. And so at the end of the day, we have speckles that are a mix of atmospheric residuals and non-command path aberration. And this is really the core of what I will be trying to correct in my thesis. And one of the big problems as well is that some of these NCPAs, some are static, so that's fine, but some are dynamic, so they evolve throughout time and during the observations. And there is low and high special frequencies, which makes them extremely challenging to correct. First, because we don't see them in the AO loop, and then because they actually evolve. So yeah, try to see NCP as like identity theft. They pretty much have, they want to be like planets, but they're not that cool, so they try to get attention. Anyway, how can we solve this problem? Well, the approach that I'm taking is to go through the reference of the wavefront sensor. And why is it such an important thing? It is the linear point of conversion that drives the correction of the whole AO system. It really is the calibration point, and we really try to minimize the error aberrations by having the reference getting basically the closest, having all of the including all of the aberrations, sorry, and including the non-command path aberrations. And before I dive into finding solutions, let me introduce you the SKEXO instrument, which is an instrument I've been working on. It's a two-stage adaptive optic system that is located at the Super Telescope in Hawaii, which is an 8.2-meter telescope. It's a actually really big one. You may not see, but it's actually really, really huge. And it's pretty much the state-of-the-art instrument for both science and instrumentation developments. Here's an image of what is the type of correction that we do. On the left-hand side, you have, without any adaptive optics, in the middle, you have the first stage AO. The second image, sorry, the right-hand side one, is when we have the correction with SKEXO. All right, so the NCPA problem. The question is, what is a good reference? What, as I said, it's all of the NCPA problem is a calibration issue. So what is the point of conversion to the AO loop? And in other words, what is a good reference means what is the ideal reference? What gives a flat wavefront corrected from all of these NCPA? Well, in real life, nothing is ideal. So actually, the perfect correction is not attainable because of numerous limitations, such as the number of actuators, the loop frequency, different sources of noise. Anyway, but then it is still necessary to define the reference in every AO system. Usually the reference is measured with an internal light source before on-sky observations. but the ideal reference is continuously evolving with time. And so there is a need to continuously measure the reference sensor reference on Sky. And so the goal really is to find what is the closest from the ideal reference to have the AO loop converging towards an aberration-free state without speckle. Now let me introduce you the Doctor Who algorithm, aka the NCPA Doctor. It stands for Direct Reinforcement Wavefront Heuristic Optimization. Yes, it's hard to pronounce. And in a nutshell, while the adaptive optics loop is running, Doctor Who updates the wavefront sensor reference with lucky imaging on the focal plane image. And why the focal plane? Because this is really the only way where we can see the impact on the NCPA. Okay, now how does it actually work? Well, as the adaptive optics loop is running, we save telemetry, we save data of both the focal plane data and the wavefront sensor data. And then the first step is to synchronize the streams. Let's say, for example, on a 30-second time scale, you have 2 blocks of PSF and wavefront sensor, and you really synchronize them, and both of them are correlated as well. And so and then from that, we have the core of the algorithm. So then the second step is to measure the quality criteria on this block of 30 seconds. And so the quality criteria can be whatever you want, whether it is the stroll ratio, the contrast, the intensity, you name it. The next step is to take the best X% images, a fraction of the best images, and this is where the lucky imaging comes from. So here, let's say the best 10% images. So then we take because there is this synchronicity, we take the corresponding wavefront sensor measurements, and then from all of this 10% measurement that correspond to the best focal plane images, we average them, and this is how we get the new reference that we apply on the wavefront sensor. And this is really the only thing that has an impact on the AO loop. Everything else is transparent. So we have the reference update, and then there is a direct impact on the PSF, and the Doctor Who iterations can keep on going. Now, let me show you some results. First, I did some simulation tests I will show you here just the proof of concept with the Compass software, which is an end-to-end adaptive optics simulation tool. And I simulated a SCEXO-like instrument configuration. And so what I did is that I injected 30 nanometer RMS of studied in CPA on the focal plane, which are a random combination of the first 12 modes. And so here in blue, you see what I injected, so what the wavefront sensor does not see. And in purple, you have what Doctor Who finds. So you see it's almost perfect correction of what I injected, which is exactly what we want, because the wavefront sensor does not actually see it, and yet here it completely recovers it based on the focal plane images. And so each injected mod here is almost perfectly recognized and corrected by the first iteration. And we have almost over 80% of reconstructed and corrected in CPA. Now let me show you some on-sky results, which is the juicy part. So the results that I will be showing here are on-sky observations with SCEXO, with a 10-minute run with 20 Doctor Who iterations. I used visible observation at 750 nanometer PSF, non-pornographic images, with the Vampires instrument. The observing conditions were actually pretty good that night, with a CM of 0.5 arc second and almost no wind. And because in real life the stroll ratio is actually pretty hard to measure, I introduced a new quality criteria to quantify the evolution of the PSF quality. And this is the flux concentration. And in a nutshell, as its name is, it really measures the concentration of flux in the image. And it's pretty much just the normalized norm of the pixel value. All right, now let's have a look at it. So on the left-hand side here, you have the pre-Doctor image. In the middle, the first iteration, and the right-hand side, you have the 20th iteration. And so you see already from the first iteration, you have something that really looks so much better than the first one and closer to the airy ring. And on the right-hand side, you have something that really looks far better than the airy ring. And if I plot the flux concentration with the evolution of the flux over this iteration, we really see that the first iteration is really where we have most of the correction happening, and we have really a big game that keeps evolving and getting better. And what I found in that case is that the biggest aberration was actually the focus, with an amplitude of 13.9 nanometer RMS. All right, now regarding perspectives. I started working on several things to upgrade the Dr. Who algorithm. And one of the things that we want to do is to use it not only in visible, but also in infrared mode, because this is what we're also interested in for exoplanet imaging. And we want to use Dr. Who and combine it and optimize it for high contrast imaging with a coronagraph. A big upgrade that is interesting to look at is to improve the correction speed by working not only in the whole PSF, but working on different zones. And so have different parallelization of the Dr. Who loop. And then, of course, we want to automatize it so that it can run in a routine way on Sky. So, Dr. Who is great. Dr. Who is robust. It is flexible. It does not have any linear assumptions. So the good point is that it is compatible with non-linear wavefront sensors, such as the pyramid. It does not rely on any model. So so it can be compatible with other wavefront control algorithms, such as EFC. There is no action on the AO loop besides the reference update. It does work on faint star, and NCP are recognized and compensated for. The downside of it is that it does need a fast focal plane camera, which is what most high contrast imaging instruments do not actually have. There is a need of fairly decent atmospheric conditions, because otherwise we're saturated by the atmospheric residuals, and there is numerous ways of improvement. So now let's see how Dr. Who actually fits back in our goal, which is to image further planets. So really the goal is to get better images in contrast, especially of exoplanet system. Now let's go to my next section, which is on planet formation. And I will be focusing on beta pictoris. And first, let me tell you how planets form. So first you have basically a planet into a nebula, and you have a massive accretion disk that appears with basically a huge amount of gas and dust that then evolves with different gravitational instability into protoplanets. This is a real image, by the way. And then there is debris, then it evolves into a debris disk where you have second generation of dust that results from collision of planetesimals and even planets sometimes. And this is where I will be focusing on with beta pictoris. And then you have fully formed planetary systems. All right, so now I'm happy to tell you about the beta pictoris system, and I got really hooked about this system because it's a pretty young system where we have a disk. Here, that as you see, we have one planet that is directly imaged, and here is a GIF. Oops. Sorry. Well, it doesn't work, but here you actually see the orbit because it's been observed several times throughout the year. So you see the orbit of the planet itself. And the planet was first observed in 2003 and published in 2009. And well, there is this, there is two planets and a second one that was discovered with radial velocity. And it's been observed extensively throughout the years, and it became a really emblematic system to understand this planet interaction and to understand planet formation and evolution processes. And so we observed beta pictoris with the NEAR instrument, which stands for New Earth in the Alpha Centauri region instrument. Try to see NEAR as like SkyCO, like an extreme adaptive optics system, but in the mid-infrared. And so NEAR is an instrument that works in the mid-infrared centered at 11.2 microns. You have a coronagraph and a secondary adaptive optics secondary mirror. So basically you have high contrast imaging. You have an angular resolution of 0.3 arcseconds, and it was a 1 year long program that was mainly focused on Alpha Centauri. Some other studies have been published, and here today I will be presenting you NEAR observations of beta pictoris. And I would like to stress the fact that it is unique data of this system in high contrast imaging in the mid-infrared, and it's a great preparation for the James Webb instrument data. All right, so no more suspense. Here are the images of, like, real images of beta pictoris with near. So you see there is a disk that is very well resolved. There's beautiful structures. Here is where the planet was expected to be. The top part is just direct stacking of the images. Down part is angular, bottom part is angular differential imaging. And so I used the speckle software to reduce the data. And so we did not actually detect the planet. However, we looked at the contrast curve, and here's the result of it. So the contrast limit, taking into account the chronograph transmission, which is at the expected separation of the planet of 30% at 0.3 second, which is not so great transmission. And so we end up with a contrast of 5 times 10 to the minus 3, given that the simulation tells us that the flux of the planet was estimated at 10 to the minus 3. So we do not detect the planet, mainly also because it's super, super close, given the telescope resolution and planet is at 1.2 lambda over d. All right, so given this contrast, we still we use this contrast to find the flux that we get and try to see if we can put any constraint on the atmosphere of the planet. So here you see there's near-infrared spectra of beta pictoris, and the gray one is the model, and you see here the green part is what we have with Vizier, and this is clearly not enough to put any constraint on the atmosphere. However, then the question becomes, can we look at possibly dust around the planet? Because in the mid-infrared, we're actually sensitive to temperatures that were not sensitive in the near-infrared. We're sensitive to far colder things, and especially the dust. And just as an example, a black body at 260 Kelvin would peak at 12 microns. So then the question is, can we say anything about the presence of dust around the planet beta pictoris b, given this flux limit? So assuming there is dust around the planet, which amount of dust reproduces this flux upper limit? And there is another studies that looked at that as well, that attempted to constrain dust in the Hill sphere of the planet by McCook and Worthy, published in 2021. And so they have a very different starting point because they start with visible data. They looked at the whole dust inside the Hill sphere, and interestingly, actually, we end up with the pretty comparable results. So how did we do that? We have several hypotheses, very simplified hypotheses. So just as a reminder, the planet to start distance is 10 AU. So we're very far, 10 times further than the Earth's distance. We're very, very far from the planet, pretty close regarding their altimeter. So the planet temperature is 1700 Kelvin, and there is the temperature and the distance is here coupled for the dust. And so we look at the dust within the Hill sphere, the Hill sphere, which is 2500 Julian radius. And basically we look at shells, like spheres of dust around the planet at different distances. And we neglect the stellar heating because we're pretty far away. And here is why. If we take here is the temperature plot of one single dust grain. And so what happens is if we look at the distance of this dust grain, we're pretty much dominated by the planet up to 100 Julian radius, and beyond that we are dominated by the stars. So we can pretty safely assume that we can neglect the stellar heating. Regarding the dust size itself, well, we assume that there would be different sizes, but we impose, for simplicity, the size at 2 micron, which corresponds to lambda over 2 pi. And it also happens to correspond to the blowout size of the system, which corresponds to below this size. Basically, any dust would be ejected by radiation of the planet. Another hypothesis is that we assume that once you go, that the dust corresponds to a black body emission weighted by an absorption coefficient QAPS calculated with mid-array from the Greater Radiative Transfer Code. And here then we have the flux emitted by one single dust, and here we have the Planck function, and here is pretty much the ratio of the surface of the dust and the surface of dust to planet distance. And from that, we can have the total amount of dust from given that we have the flux limit and the flux of one single grain. So, what does it actually mean then? So we have, this is a plot that shows the distance to the planet, and on the left-hand side, you have the mass parent of the body. So let's have a look at the green line here, which corresponds to the mass. The green horizontal line corresponds to the results of Matthew and Worthy, and there is a factor 4 difference. The blue vertical line corresponds to the Roche radius, which is just here for an indication. And so what we see here is that if all the dust was within the Roche radius, the amount of dust that would be around the planet would correspond to the collision of an asteroid of 5 kilometers of diameter. On the right-hand side, you have the size of the parent body, and that corresponds to the red curve. So, in conclusion, there is, well, very little dust around the planets. I show here what is the Saturn's rings mass, which is within the Roche radius, and we are 700 times lower than that. So there is very little dust around the planet. Definitely not enough to have the equivalent to Saturn's rings. Now let's have a look at the disk itself. So you see here, I mentioned a few structures, and there is this clump that I will be focusing on, the southwest clump. And then we see another very obvious clump here. There is other clumps, but we definitely need further observation to really confirm their presence. And the clump 1 was actually previously observed since the first time in 2003. And the question is then, given there is several observations of this clump over the years, can we say anything about its nature? And we can, to answer this question, we can go through the study of its dynamic at different epochs. And so there is 5 archival data from 2003 to 2019. And given the 16-year-long baseline, the question is, how did this southwest clump evolve? And can we find out what its origin? And Lee et al. 2012 studied T-Rex data, and they found between these two epochs a 2 AU displacement. And so what I did is that I observed and studied the Vizier data to really measure precise position measurement. And so if I get to plot the surface brightness of this clump over time, we see here that there is a clear motion of the clump onward with time. Before going any further, let me just stress here that we have different instruments, different qualities. We have very heterogeneous results. We have clumps that is fairly wide, so it's really challenging to really measure a precise evolution over time. It's really, really difficult. Anyway, so let's see how this is the evolution of the position, the projected separation of this clump over time. And so we fitted we assumed first that we have a circular orbit, which is a hypothesis that we put to really simplify including constraint. We did a chi-square minimization, and from the starting point we plotted the Keplerian orbit, and it clearly fits here the orbit. So we can safely say that the south clump in Keplerian is in Keplerian orbit with a semi-major axis of 56.1 AU. All right, so now that we studied the position of this clump, what can we say of its possible origin? Could it be coming from a giant impact? Well, if it's coming from a giant impact, basically we would have different dust orbits that we all meet again at the periastron that would be fixed with respect to the observer. And that is not what we see because we have a clear motion. So we can, it's not coming from a giant impact. Then could it be coming from a resonance with the planet? Well, we try to see different resonances, a 3-2 resonance and a 2-1 resonance. And it could possibly work with the green one, but it not really perfectly. So we do have we do not have a resonance with the planet. So we're left with two possibilities. The first one, it could be like this clump could be the planet's Hill sphere, and it's of a yet to be detected planets that would have a possible mass of 3 Jupiter masses. So that's a possibility. Another possibility would be that this clump here could correspond to a vortex. And in fact, I didn't mention it, but we see some correlation with CO gas observed with ALMA. And so a vortex corresponds to a maximum amount of pressure, and that could be a possible option. So in conclusion, we have unique data in the mid-infrared of beta vectors in high contrast imaging. We do not see any planets. However, we put constraint of a circumplanetary disk around the planet. We studied the southwest clamp evolution, and we find a Keplerian orbit of 56.1 AU. Its possible origin could be that it could be the Hill sphere of a yet to be detected planet or a vortex. And the main point here is that we also need further observations, and James Webb will be far more sensitive and stable to better understand the origin of the clump. METIS, the METIS instrument on the ELT, will provide a far greater angular resolution. Now let's jump to the next section, which is on atmospheric characterization. I'm a big fan of Master Uruguay. It says there's no coincidences in this world, and I will show you how this is actually linked with what we have seen before. So why do we study atmospheres? Well, atmospheres can give us information on how planets formed and possible impacts, and we can then look at molecules such as methane, carbon dioxide, water. And I'm saying that because obviously we're looking into also in the future some biosignatures. From the atmosphere, we can also study clouds on other planets, and we can study stellar radiations, and basically look at also atmospheric escapes in some cases, and volcanoes, and of course I'm really interested into alien life, so atmospheres is a way to go for that. Now, why do I introduce that? I looked at hot Jupiter atmospheres. And what is a hot Jupiter? The first exoplanet ever detected, actually in south of France in 1995, was 51 Pegasi b. And hot Jupiters are really interesting because they are really huge planets, Jupiter-like planets that rotate extremely close to their host star, between 3 to 10 days. And as a comparison, Mercury takes 88 days to rotate around the star. So we have really high temperatures on these planets that for the hottest of them goes up to 4,600 K. And hot Jupiters and direct imaging giant planets share the same formation history, but hot Jupiters have migrated inwards. And so there is a direct connection with direct imaging here. So how do we study the atmosphere of hot Jupiters? Well, this is showing how transit spectroscopy works. So we're looking at the transit of the planet in front of a star at different wavelengths, and that gives us indication of different transit depth. That gives us indication. That gives us a spectrum. And the first week of my PhD, I joined the aerial summer school where we studied 3 hot Jupiters. I will focus on WASP 127b here, which is a very fascinating planet because it is it's very, very puffy. It's very inflated, 1.37 Jupiter radius. And its mass is a sub-Saturn mass. So it really is very, very not dense, and it's located in the short Neptunian desert. And because it's so inflated, it is the 3rd best TSM, transit spectrometric, spectroscopic metric, sorry. So it basically is a very good target to study because we have just perfect transit depth. So how did we study its atmosphere? We used the Torex retrieval code, and we used the same method that was described in the population paper of Sarah et al. 2018. And the baseline model, we had a few molecules, mainly water, carbon-based molecules, and FEH. FEH being a new line list that we had, and we put different volume missing ratio. Regarding the radius, we had it vary at plus and minus 50% of the literature values. Regarding the pressure, we also had it very different between different values. We used a model with 100 atmospheric layers, and we used radius scattering of CIE and H2H2 and H2HE. Regarding clouds, we used a simple gray opacity model, and regarding the temperature, we had it vary between 400 to 2500 Kelvin. Now, some results. So here on the left-hand side, you have the posterior distribution. On the right-hand side here, you have the results of the retrieval. The black points correspond to the data. The black line corresponds to the results spectra of the retrieval. The blue one corresponds to the water line. So we see here the water actually fits really well the data. And in fact, we have a lot of water on WASP 127b with a detection over 5 sigma. We redefine as well the radius of this planet, and we put some limits on the carbon-based molecules. Oops, sorry. Oh yeah. So regarding FEH, we tried to do several retrievals. And we tried with clouds only or with only FEH, and we tried different things to see how can we better explain what is happening on this side of the spectrum. And so we find that the presence of FEH is what is statistically favored by the retrieval. But I would like to stress that with Hubble, we have a very short wavelength coverage, and there are degeneracies, and short wavelength coverage is definitely not enough to allow us to conclude on anything, and hence the need of the aerial space mission and the James Webb Space Telescope. Another big result of this paper is the retrieved temperature that we see and compared to the population paper of Teres et al. And what we see is that the retrieved temperature is notably lower than the equilibrium temperature. And here is the plot that we have. And well, it actually makes sense that the retrieved temperature is lower, because in transit spectroscopy, we're looking at the terminator region of the planets, and which naturally receives less direct radiation than the front one, which is, and then, well, that's also indicating of possible 3D effects and possible other things. And one of the big questions at that time was, is water vapor destroyed in the upper atmospheres of inflated hot Jupiters at the terminator region? And because we find water in the 3 planets, we can safely say that water vapor actually remains. All right, now this was going a little bit all over the place. Now what? Well, how does it fit all together? How do we make more planets closer into their host stars in the EL-free landscapes? So here's, well, this is what we currently have. We can go down to contrast of 10 to the minus 6 after some post-processing, so we can detect brown dwarf and some Jovian planets, some photoplanets. We can see some dust. However, this is the current limit that we have on the spectral noise. And the fundamental photon noise limit is far different contrast, and this is what we're trying to work towards for focal plane wavefront control. And the point is to get closer to the habitable zone to be able to observe more planets closer in. And if we use the focal plane, we can go even deeper in contrast and eventually detect and study Earth-like planets. And this is what Doctor Who and other wavefront control algorithms are aiming at doing. And with the next generation of 30 plasma telescopes, we should be able to get far closer in separation, but we need to get ready for that. And so we have better contrast. We can have better contrast with instrumentation development. And the point is to have data with better SNR, better spectra, and study things closer in. So also study closer in planet formation. But with great power comes great responsibilities, and better images means we need to be able to understand, interpret, analyze the data that we have. And so there is a need to for the fields to work hand in hand together, because if we have better data, we need to be able to understand them, and we need to have a back and forth between what we are trying to observe, and how can we go in instrumentation development for that. So throughout my PhD, I used several tools that I did not develop myself, and I would like to acknowledge how great they have been for allowing me to do this research. There is the Compass software, there is Kingstone instrument, there is Speckle, there is Gratter, and Iraklis and Torex. And there is also a list, huge list actually of co-authors that without whom all of this work would not have been possible. And here I would like to acknowledge their hard work. These are all of the 3 co-authors of my papers. And this has been really a big collaboration work with big connectivity between different people. And the main point is that we definitely need each other to move forward and be able to understand things and how they are all connected to one another. Thank you for all of you to be here today. This is a big day for me, and I'm honored that you come with so many of you for this big day for me. And thank you for the jury. Thank you for my PhD supervisors that have bared with me all of this time and who have been amazing support for me, and to my mentor also, Giovanna, who is here, and thank you.
Thank you very much, Nour. You are perfectly on time, so you are perfectly on time.
I'm surprised. I think I spoke a little bit fast. I'm sorry about that. I was a bit nervous. Sorry.
So the very good point is that we have plenty of time for questions now. I will hand the floor to Vanessa first, which is first rapporteur today. Vanessa, please.
Yeah, thank you for a great presentation, Nour, and this is an impressive body of work spanning a number of different areas. So one question that came to my mind is in the Doctor Who section was how you would change your algorithm or change the metrics to expand it to coronagraphic data.
Yes. I'm very excited you asked this question because I actually have some backup slides.
Well, I promise that wasn't planned.
Wait, how does that work? How can I go? There we go. So the second season of Doctor Who is how can we upgrade it for chronographic instruments, and what I'm aiming at doing is a parallelization of Doctor Who in different zones, and I rely on this. Sorry, this is very annoying. You don't see that? I see. I'm gonna move that slightly further up. There we go. So the main point here is to rely on Fourier theory, which states that a pair of speckle in the focal plane corresponds to a sine wave in the pupil plane, and how would that work for chronographic images? Well, the whole point to really make Doctor Who optimize for chronographic images would be to take the chronographic image. So here it's written PSL, but I really mean chronographic image that we divide into different zones, and we take the core out, and we really have a Doctor Who on each of these single zones. So at the end of the day, we have different, for each Doctor Who iteration for each zone, we have different intensities. And with Fourier filtering, we can basically see what are the corresponding wavefront sensor aberrations on the pupil plane that corresponds to the pair of speckle in the focal plane of the chronographic image. And then we have different intensity zones, intensities correspond to each of these zones. And we have the different filtered wavefront sensor images that at the end of the day, we do the same whole thing for the whole Doctor Who loop. And the point is really to treat speckles individually. So really the goal is to have zones of sizes of 1 lambda over d to treat speckle individually and find out which zones where its intensity does not decrease, and then directly from the chronographic image say whether we have a speckle or companion. And my slide says that we get closer towards dark speckle technique, and the main challenge is to be able to detect very fast and very high sensitivity photons on the focal plane. And for that, we need the technology of very fast focal plane cameras, like the MKITS instrument.
Oh, thanks. So I wonder, let's imagine that you have this, MKIDS instrument or other instrument that lets you observe with sufficiently short exposure times. How, so there are multiple different timescales of evolution involved in, there's both atmosphere and instrument, and the evolution, particularly of the atmosphere, impacts the optical gain of the wavefront sensor. And so I'm wondering how you would envision deciding how often to run this procedure, so that you might capture both optical gain, instrumentation variations, while also bearing in mind that you must have a minimum or maybe a maximum exposure time on your science camera.
Yeah. So if I understand well your question is, how can we optimize Doctor Who given the different conditions and also with the optical gain that has an impact on things? I started to work on two things. First one, which is looking at different cases, like depending on different observing conditions, different settings, what are the different parameters that we want to have Doctor Who running on that would be better optimized? How can we increase the conversion speed of the algorithm? How can we optimize it for different observing conditions? And so I have data on sky data at different at basically whether we want to have, so when we have bad observing conditions, for example, we want to have not 30 seconds, but let's say 1 minute, because the diversity of the atmosphere will be such that we will be maybe limited by atmospheric residuals. So we want to go longer, but also shorter selection fraction, not 10%, but let's say 1%, because otherwise it could kind of turn bad. Second other thing is that I tried to do some time ago, which is to have Doctor Who running with some optical gain compensation algorithms, such as the CLOSE algorithm that is was developed by Vincent Dio. And so we tried with him and Ariel Bartou-Cantou, how can we have Doctor Who working with optical gain compensation. And then the thing with Doctor Who as well, we do not do any linear assumption. So I don't want to say we bypass the optical gain problem, which is not the case, but we are compatible, or I should say we do not do any linear assumptions, we only do continuity assumption. So there is nothing that's limiting us to use nonlinear waveforms such as the pyramid. And so I don't know if that answers the question.
Yeah, I think maybe just one last piece of that is, if I understood correctly, at the moment, this is something that you run once towards the beginning of an observation and keep that optimization over time. Do you imagine running that multiple times throughout an observation or continuously to keep up with optical gain? Or how would you weigh that against perhaps changing the PSF? Because that would impact your ability to do PSF subtraction if the PSF is more variable.
Yes, I have not tried to let Doctor Who run throughout the whole night. What we did, which is a pretty safe thing to do, we ran Doctor Who for a short period of time, and then we have a new reference after, let's say, 10 iterations, and we use this new reference for the rest of the night. Or if things go bad at some point with bad conditions, we may do it again. But I haven't tried to run it throughout observations. That's the goal, though. Basically, to what I have from my tests so far is that Doctor Who does never diverge. So there is, from what I see with my limited test, is that there is nothing that could go wrong with Doctor Who running over time. And we can also use possibly like a gain, for example, to basically not put the whole 100% view reference, but to put a fraction of it, so that we play it safe into being able to use it throughout the night. And the thing with KXO is that we are always here to tune the instrument for when things go wrong. Doctor Who is not at the point where we can put it, let's say, on Sphere. Well, there's no classical plane on Sphere, but let's say to like have it fully automatized and basically stop if things go wrong. This is one of the things that I'm aiming at doing, is to basically have Doctor Who being smart enough to change its own parameters to adapt given the focal plane images that it sees. So if the flux concentration keeps decreasing, then it could put back the initial reference, for example.
Great, thank you. And I know there are many other members of the jury, so I won't take all of the question time. Thank you very much.
Thank you.
Thank you very much, Vanessa. Now the second rapporteur, Marcel.
Muted, Marcel.
I forgot, sorry. So I was saying that it was, I'm impressed by your work. It's very impressive, you have a very wide field of expertise now, and from instrumentation to diverse exploitations of this instrumentation. And I won't be too long anyway. I found also the presentation very pedagogical, so thank you. And I will go straight forward to the questions. And my first question was already asked by Vanessa, but it's okay. And I have another one about also about Doctor Who. I have a couple of questions about Doctor Who. And the first one is curiosity. Did you try some other kind of selection of the images then? I mean, did you find something else than 10% of selection of the 10% best images? Did you try, for example, twice more, 20% or 5%? And is there any fundamental difference, or is there, or the optimum is quite flat, and it is not that important to find the good number of selection, because it is not easy to select, I guess.
Yeah, thank you for asking. I started doing my tests with 30 seconds blocks at 10% selection fraction, but I have, well, the journey to have Doctor Who work was pretty long, so it's only at the end that I started to play with this optimization. And so I have some on-scale data with different selection fraction and even bench data, where I see that when the atmospheric conditions are fairly good, I can go far shorter in time. So we have, let's say, for example, on 5 seconds time scale, you can select the best 1% image, and basically that would increase the conversion speed of the algorithm. And that really is dependent on the atmospheric condition, because the bigger the atmospheric residuals and less we're sensitive to the NCPA, but rather saturated by the atmospheric residuals. So the point here is to basically, how can we optimize the selection fraction and the length of the algorithm depending on the atmospheric condition, but also it's actually far easier as well to do that in visible light and in infrared light. And so when we're in infrared light, we need to go also a little bit longer in time, because we see less things. So the optimization is still something that I'm working on, the different parameters, and this is something that I'm trying to explore what makes it converge faster, and this is still ongoing. And I hope to have answers to that coming very soon with the data that I have.
Mm-hmm. Do you think it could be linked to the magnitude of the object you're observing? I mean, not the one you're observing, but the one you are using for sensing. Also, my other question linked to this is that did you try also different regime of amount of photons? I mean, did you go to different kind of object magnitudes and guide star magnitudes?
Yes, so for on SCEXEO, because we usually look at stars that are pretty bright, we don't have a laser guide star, so we look directly at our target directly, which usually for SCEXEO doesn't go over magnitude. Well, for science cases, we barely go over magnitude 10. For instrumentation tests, we try to stay very bright. I have not done tests on very faint data, very faint targets, sorry. I think the faintest that I've been doing was maybe magnitude 4, which is still pretty bright. In theory, it would work on faint star. And there's nothing that really prevents. All that we need is to still have enough photons coming to the wavefront sensor, and then we can, on faint stars, we need just to have, we would need to have a longer exposure time of like a longer iteration of the algorithm to get more fast, like focal plane images, to then have basically a wider range of possibility for lucky imaging. So when the atmosphere would by chance correct the NCPA. So in the case of a faint star, that's that we would need to have a longer iteration of Dr. Who.
Okay, thank you. And I have a technical question as well for the simulations. So how did you simulate the fact that the reference is not ideal and is evolving?
In simulations, how did I manage the fact?
Yes, did you add a statistical NCPA or what?
So what I know, I only added static NCPA. So that's something that I've been wanting to work on. I got a little bit burned out of the software simulation algorithm, to be fully honest. That was one of the ideas to see when basically how the NCPA are evolving, how does it have an impact. I did not end up doing it, and I only stayed with static NCPA, which makes it also far easier to correct on simulation. So yeah, that's something that I wish I did.
And I have a question also about the pyramid for SCEXEO. So you worked with modulation of the pyramid that is of a 3 lambda over d, 3 elements of resolution, so, which is not. So I was expecting maybe something less. So why do you need to modulate that large? Since the wavefront is already corrected, one could expect maybe a modulation which is just of 1 or 2 lambda over d. So, but you need 3. So is it? Why just because to be prudent?
So the modulation varies. So we set the modulation radius during on-site observations. If the conditions are good, we may not need up to 3 lambda over d. Sometimes we can go down to 2 lambda over d. I think there is even the option of going down to 1.5 lambda over d. To be very honest, I don't exactly remember. However, when we are in worse seeing conditions, because the pyramid behaves in a pyramid way, so we need a wider radius of modulation. But why does it only stay? Why does it stay at 300 lambda over d? I'm not an expert on the modulation of the pyramid. That doesn't shock me. That doesn't seem big.
No, it's not that big. You're right. But okay, I was expecting a little bit less. But okay, it's not that fundamental for the work you did.
Yeah, and
okay.
and we can go with smaller modulation radius as well. And in fact, the fainter the planet, the star, sorry, the wider the modulation radius, and the brighter it is, and we can go in smaller modulation radius. There has been work at SCEXEO to see how the pyramid works without any modulation, or with very, very tiny modulation. This was done by Christophe Clergeon, and this is actually something that is extremely challenging. Yeah.
Okay, and do you think we can adapt? You can generalize it to any other kind of wavefront sensor? I mean, for example, Shack-Hartmann or Zenik wavefront sensor.
It is wavefront sensor independent. It can work with the pyramid, the curvature, the Shack-Hartmann. All you need to have is a wavefront sensor, and they all have a reference, and so it is compatible with any wavefront sensor. The issue is not so much the wavefront sensor; it's more we need a fast focal plane camera because we need the synchronization, and that's something that is not so present into most of the high contrast imaging instruments. It is present, however, on SCEXEO and on MyGAOX.
Okay, perfect. And you say in your manuscript, you say somewhere that Dr. Wu is compatible with other NCPA methods. So
yeah.
Did you have the opportunity to test this?
Well, I started, and I got distracted by Pedapic, so one of the things that I have been discussing with another postdoc on SCEXEO is how can we combine Dr. Who with other wavefront control algorithm? Here is LDFC, linear dark field control. So the bright side of the image is used as a wavefront sensor, focal plane wavefront sensor, and the dark hole side is where we can use basically this whole area as a zone of Dr. Who where we want to minimize the intensity. Yeah, I think I didn't mention it to Vanessa as well, but the big difference with chronographic images is that we don't try to maximize the flux concentration or the shell. We really try to minimize the intensity to have better contrast. And so that's what I started working on, is how can we minimize intensity on the dark zone. And because it is completely transparent to the AO loop, and it does not rely on any model, it does not need to use the DM. And so that's something that makes Dr. Who very prone to have some friends in the wavefront control realm.
Okay. No, it's okay. It's okay for me. Thank you.
Thank you.
Very much, Marcel. So now we'll start with the first examiner, Wood.
I'm sorry not to be here with you. I really appreciate your presentation, your manuscript, and your perseverance in this thesis. We all know that instrumentation is tough, and you did many other things from study of this and also atmospheres, and it's really great to see it all coming together in your nice presentation. You can stay on this slide actually, because I was wondering also mostly on Dr. Wu, so sorry for the lack of diversity in my questions as well, following the referees. So on this slide, you said, you're keeping the speckle and your criteria is to minimize the flux. My question is then, you still need to have a criteria on maintaining a nice PSF for the planets. So how do you envision to combine both? Because if you only try to do speckle, you might destroy the sharpness of the PSF.
So the thing with the planets is that it would so in that case, ideally, what we want is to use Dr. Who in different zones. And so we would look at which zone only gets better. So we want to basically, if you want to there is the zone where there would be the planet would never go darker because the planet is there. So it's not a speckle. And so that's how we would differentiate between what is a speckle to what is a planet. And so because the planet signal would still remain depending on the atmospheric conditions, that is not incompatible with still seeing the planet. I don't know if that's I'm not also hearing super well. I don't know if it's just me, but
well, I think it's a complicated problem, so my question is not that easy. So in case there is a planet, indeed, you can play some tricks. If there is no PSF-like thing in the field of view, I think maybe we need to get some information from somewhere else. But that's, yeah, I think it's not so easy. I think it's an area, but you may need additional information somewhere. Yeah, but you answer my question. So I was wondering if you tried to simulate ELT, where in the context of phasing residual, there is much more mode to deal with, and getting the proper diversity to get Doctor Who working, even if without coronography, might be a bit challenging. So you mentioned speeding up things, but did you also try simulation on this scale?
So it's really funny you asked this question, because I asked this very question to Olivier this morning at 7 a.m. And the short answer is, I don't know. And the philosophical answer is, who knows what will happen on the ELT. It's such a mysterious world. The more complete answer maybe is that well, with the ELT, we have so much more actuators. There is the titanium effect that will come in, and there is just a lot of mysterious things. So how will Doctor Who fit into all of that? I'm nearly tempted to say that it will be different. Did I do any tests? Unfortunately, I did not. Skexeo was already challenging enough, but yeah, this is something that I'm very interested in, especially because we need to get ready for that. And unfortunately, I actually don't know how things would behave. I'm tempted to say that there is no reason for things to be different, but also that this answer just emphasizes my lack of knowledge on ELTs.
Maybe you have work for a postdoc or something. It's a big work anyway. Maybe one hint. I was also wondering if in case you can basically add more diversity by adding some defect in your deformable mirror, small but known, and to increase selecting to increase rapidly the diversity. And I was wondering if you tried this already on Skexeo.
Yes, not on Skexeo, I tried with Compass. I basically tried to poke the GM to basically make the conversion faster, mainly because doing Compass simulation, it takes quite some time, requires GPU. It's it's an end-to-end AO simulation, so it takes quite some computational power to simulate the atmosphere and so on. So yes, I did try to basically put some random combination of modes on the DM to see how, basically to make it converge faster, and it worked. And actually, I think it's possibly how I got the main results.
Okay, by a large amount, like a factor 10, or?
No, that was that was actually pretty small. How much was it? I think it's written somewhere in my thesis. I don't exactly.
Back. No problem. So good. Glad you tried, and thanks for your answer.
Thank you for the question.
Thank you, Maud. Second examiner.
Yeah,
Olivier.
Yeah. First, thanks for the very clear presentation and a clear thesis. I have read it it was very nice. I will not ask a question about Doctor Who. You learn already a lot, and I'm really not a specialist. But I will ask about Betavic, an old friend. And the first question I have, so when I saw the figure 4.3, I said, great, they will detect the Betavic B. And at the end, it was not the case.
Yes. How sad.
So, first question, why such, I know the answer, but why you didn't detect it?
Well, one of the reasons why the planet was not detected is that it's actually extremely close to the star. And the chronograph, the AGPM chronograph, has a, sorry for the judgment, pretty bad transmission at this separation. It's only transmitting 30% of the light. And because we are at only 1.2 lambda over d of the telescope resolution, I suspect that's why. Also, the planet itself is at 1700 Kelvin, and we're in the mid infrared where we are sensitive at colder things. Although we did suspect to be able to see the planet, and well, we did not. The contrast that we have is not good enough to be able to see the planet.
Okay, I thought that the disk itself would prevent to see the planet.
Well,
and what's the limitation in terms of noise, neural noise, the photon noise from the disk itself at this position?
Is your question as in like if the dust in the
there
disk
is already the disk, yeah. There is already this.
That would hide the planet?
Yeah.
Well, possibly, and that's also why we looked at circumplanetary material around the planet, because could it be that we actually just see the dust without being able to see the planet? And so that's how we did this test to see what would be the amount of dust that would correspond to the flux upper limit that we have, which is in that case, from the contrast that we have, it is not so informative on whether there is so much dust on it or not. And yeah.
Because if you go back to the image just before, you see that there is some dust at this position.
Yeah, well, there is definitely dust. Here we're also in angular differential imaging, and in PCA of selection of like first 10 modes. We see something. The contrast that we have is, well, we see there is dust, and we see there is planets. We don't see anything very obvious, and that's how, like, from the contrast curve, we do not see. Yeah, sad, very sad.
And you mentioned that with James Webb we will not see the planet.
Yeah, so
likely, you say likely. And why did you say that?
Because the telescope resolution is defined by the diameter, which is 6.5 meters for James Webb, and we are at 0.3 arcseconds separation for the planet. So I would expect it's not in, like, the resolution of James Webb may not be enough, although we could try. I would love to try.
It will be tried.
Yes, well, there is MIRI data that I think have already been taken in December. Would be very curious to see near spec data as well, and see, if we can actually see the planet with James Webb. Would expect the apparent separation of the planet would be too small with James Webb, but who knows?
Well, we have, I think, a specialist here about this 4-phase masks, which allow to go to lambda over d. So from simulation, I think that it could be seen. Could be, but my worry was about the disk itself, which could be higher in terms of flux. So that's why we could observe the disk when the exoplanet is not there, and again observe it with the exoplanet, so that by making the difference, we may end up with seeing the exoplanet.
Yeah, that would be really great to see at different wavelengths as well, to see different contribution of the disk, and when, especially in the near infrared, and see you can see the planets.
It's not the same color graph, but as it is at shorter wavelengths, they are the same performances as what we have at mid infrared. So,
well, if you get some data,
I'm sure you will. I'm sure. So thank you. That's this chapter I was focusing on.
Thank you.
Next.
Thank you very much, Pierre-Olivier. Now I hand the floor to the advisors, and I will start with the most remote one. Olivier.
Hello, can you hear me?
Yes.
Yeah, so thank you, Nour, for the presentation. As I think everyone understood, Nour's PhD covered an unusually wide range of topics. I mostly helped her with the instrumentation parts of the PhD, and so I'm going to actually ask a quick question on that, and it's building up from the previous question. What happens with a larger telescope? And I'm going to ask you, Nour, to comment on that. And the challenge with a very, very big telescope with an ELT is that there are a lot more modes in the wavefront than that can change the PSF. So what do you think that does in terms of the convergence speed of your algorithm, and maybe what direction does that push you into?
Yes. So one of the thank you for asking. One of the input parameters of Doctor Who is the size of the selection zone. So the size at which we basically do the lucky imaging. So we could only focus because when at the center we look at the first mode and the higher the radius in the PSF, so I should do that. And we're going at higher modes. So the central part is where we have the lower order modes. So we could only just focus on the lower order modes. And that's also really dependent on the deformable mirror itself and how and also the resolution of the wavefront sensor and how we could basically have a greater selection, have a greater zone in the PSF and have a basically higher mode to correct. And we definitely need to have a high resolution wavefront sensor to be able to detect these modes, and also to be able to correct them, we need to have a very high number of actuators. We cannot correct, I mean, the number of modes that we can correct is really dependent on the number of actuators that we have, or the size of the actuators.
Do you think this is, it seems your comment is pointing to the need for Doctor Who by zone on the larger telescope. Is that what you expect, that you need to implement the Doctor Who by zone for a larger telescope?
I expect Doctor Who by zone to be far more efficient, far faster in terms of conversion speed, and already within the current very large telescopes that we have, that would be a game changer to have Doctor Who in zones, because we would be able to really just see the PSL and correct the speckles individually. So even more when we go on larger telescopes such as the ELTs, looking at zones on themselves will basically be able to correct, I guess, modes, given that we look at pairs of speckles, and with Fourier transform, we can trace back the reference that we need.
Okay, and my last question is tying things a little bit between different chapters of your PhD. You did some spectroscopy characterization. And that's clearly also what we want to be doing with direct imaging more and more. But when we do spectroscopy characterization, the spectrograph usually takes very long exposures. So how would you do? Do you have ideas how you would do Doctor Who if you're trying to do spectroscopy? Are these incompatible?
Well, what we currently do with Doctor Who on SpecSeo is that we use the fast focal plane camera, and we have actually, so there is the Caris instrument that does some very low resolution spectroscopy and very long exposure time frames, 15 minutes, 20 minutes, half an hour. And we still can use the fast focal plane camera that is ideally very close to the science camera, that would take into consideration all, like or most of the NCPA. So for spectroscopy, that is compatible with it if we still have this fast focal plane camera that is close to the science camera, and we would correct most of the NCPA from this one, but still acquires long exposure time frames, like long exposure frames for spectroscopy.
So how do you choose which light goes where?
Well, ideally, you would need an MKIDS camera that is a photon counting camera, where you would need very little photons to go there, and most of your photons would go to your science camera. And from like this type of camera, the MKIDS camera, you, from the very few photons that you have, you could still gain a huge amount of information without sacrificing the information that you send to your science camera.
Okay. Yes. Yeah. Yeah. I think that's right. You need to share the light, and low noise cameras are going to be absolutely critical to optimize that. So thank you. I don't have any other questions, and maybe I'll let Anthony ask some questions and give some comments.
Yes, thank you, Olivier. You're right. Now it's the turn of Anthony.
Okay, so yeah, I don't have any questions, but I would like to say that I'm very happy to be here today to hear your presentation, which was really clear. It was my 5th time. It was perfect. So after this 3.5 years working on these topics, a bit less together, I think it's obvious to everyone that being able to carry out these 3 topics in parallel, switching from one to the other with very different techniques, very different methods, different people also supervising you is not easy, and so it's really an achievement, I think, to be able to do that in the time frame that is allowed by the thesis. So I think this is very important, and it's really the characteristics of your work in this thesis. And but in the end, you managed to produce very good science with these 3 papers. So I think it's remarkable. And to make it clear also, I would like to say that it was your decision to include observations in direct imaging, in transit spectroscopy in this thesis, which at the beginning was really just instrumental. So I think it's important. I think I'm fully in line with your philosophy of doing research to combine instrumentation and observation. So I think to me it's really important. And I think to many of us also, of course. And also the fact that you are interested in these 3 topics, it shows your level of curiosity in the field of exoplanet at large. Again, I think it's important. What I witnessed is that you are not afraid of getting involved in new projects, even if sometimes it's very far from the comfort zone. So this is clearly remarkable. Also things that I would like to say that are not in your presentation is that working on Doctor Who in particular in instrumentation, as some of us know, it's quite a lot of time spent on the instrument, on the telescope. So it's not like you press a button and you get the result. You have a lot of things to do. And as you said, you also have some data that are not yet exploited. So you will have to go into this data. You also have data of observations with XAO that you did not mention. It's also part of your work in this thesis. In particular, on 2 very interesting objects that are disk-forming planets, Calcium 15 and PDS 201, if I'm correct. So I'm looking forward to see this data published sometimes, hopefully. And also, I think I would like to add one thing that you did not discuss is your implication in and your willingness to push public outreach and your willingness to make sure that people who do not have easy access to science will have access to science, and you have already planned project for the next month in Africa, in India. So this is again something that I'm very impressed by you being able to do all these things. So yeah. Also, maybe just a point about the last 2-3 months, which were really intense by writing the thesis, implementing the correction in the beta-pic paper. It was intense but very motivating for all of us, I think. And I really appreciated that, even if it was a bit, intense, I would say. So yeah, and maybe one last point, I would like to thank you also to bring your fun and happiness in the team when you are here, and a positive attitude also when you are here at thèse. And maybe last but not least, I would like to make sure that in the last weeks, in the next week, or month, we will keep going with our discussion about other topics, if you will. Yeah, so thank you very much.
Thank you very much. Thank you very much. So you understood you still have a big program.
Yeah.
Okay, and now we have a third but non-official supervisor, Giovanna Tinetti, who is a guest of this jury. So please, Giovanna, it's your turn now.
Thank you. Well, I'm echoing the words, I think, of all the participants to this jury in saying that Nour, you've done quite a remarkable thesis, remarkable in many ways, as many of you remember have pointed out, remarkable because of the breadth and the depth of what you covered. It's very unusual to have PhD students able, during the time frame of the thesis, able to cover really in-depth instrumentation, observation, and modeling, and on top of that, different type of techniques. So to me, this is the first time I'm seeing this, and so I'm really off. So I will start with this very strong statement. I really enjoy reading your thesis, also because I think one could read your voice in your thesis, which is also great. It wasn't a sort of extremely well written, but a little bit more standard thesis. One could hear your enthusiasm in what you're doing and your unique perspective to how you do things. I thought that was great, and so I really enjoyed reading that. I don't want to ask you too many questions because many other people had the opportunity, and of course we had the chance of discussing things in past years. But maybe spending a couple of minutes about atmospheres, given that you haven't really received any questions about atmosphere. So I feel the need, in a certain sense, to tick the box here. And you analyzed some atmosphere attributors through the transit technique. And quite rightly so, your thesis, on one end, you're showing how much you extract out of this data, but also how much more you would like to extract. And you're sort of referring to GWSD in particular, like strong variable. So GWSD is here, is doing wonderfully. So what would you like to do with GWSD about these atmospheres that you look at with the carbon?
You said what, Steven?
What kind of observation you would like to do with GWSD, given that GWSD is here and it's not as limited as Hubble, at least for exoplanet atmospheres?
I want to see this one, what's 127b? And of course, beta pictures. I think what's 127b, I'm actually super curious to see. I'm sure there will be data of this planet coming. There will be like observing this planet at far greater wavelength as well would allow us to see far more molecules and break a lot of degeneracies, and especially regarding FEH, which there have been a lot of papers discussing whether or not there is FEH in this contributor and the two other ones. There is really a need to better understand what is the dynamic of this atmosphere, because also it's so puffy, so inflated, and it has such a great TSM. Like I think it's really a perfect target, and I'm very excited to see the data of James Webb on it, to really see if we can also from like radiation transfer things, if we can see some maybe 3D retrievals or not 3D, like 3D modeling, and from what we basically compare the modeling that we can gain with things such as XRM, to then compare with the Torix retrieval with far more molecules and maybe more complex chemistry, to see what we can understand of this planet that is just so unique because of its so low mass and low density, and how can it help us understand the physics and chemistry behind these atmospheres. There is another thing that I'm actually really excited for with James Webb. It's the TRAPPIST system with so many planets, right? There's 3 planets in the habitable zone, and well, obviously they're transiting, and we want to see if there is an atmosphere over there. They're the best targets, to my knowledge, the best target for possible habitability, or at least to detect biosignatures. Will we be able to answer this question with James Webb? Probably not, but that will definitely help us in understand the physics and chemistry of telluric rocky planets that are orbiting in habitable zone of their star. There is actually great documentaries that I watched a couple of nights ago to get excited, and there is a bunch of transiting planets that are ocean worlds, and some of them are like really fascinating planets, 55 Cancri with like massive volcano activity. Like, planets are just so diverse and different. There's so many of them that are so different from what we see on our solar system. There is a bunch of them that would be really fascinating to study their atmosphere in transit spectroscopy with James Webb. Yeah, I think really TRAPPIST maybe even more than WASP 127b for me.
Thank you. I don't have another question.
Can I say one word? I think when we got all excited about beta peak over the last 40 years now. I mean, you would know better. And now we found, I think, and Anne-Marie Lagrange mentioned that the TRAPPIST system will become what beta peak was for the last decades. And so there is probably so much that we can learn on how planets form and dynamic with this system of several rocky planets. So yeah, I think that's probably going to be I don't know, the focus of the exoplanet field in the next decade.
Thank you, Giovanna. Okay, so I'm the last one. I have a few questions. Some of them were asked, some others not. The first I have is on WASP 127b. Can you show the posterior distribution again, please? Yeah, so some parts of it look quite bad, actually. And I was wondering, what is the reason why we have these correlations and these kind of expanding blobs? Is it because the wavelength range is too short?
So
is it the main reason, or there are some other biases that you have not mentioned?
There surely are biases that I don't know. My main answer here is so you're talking about carbon-based molecule and ammonia. This is in fact really bad. My answer here really is about the fact that we have degeneracies with this short wavelength coverage. And the abundances we don't actually see here, but if you look on the thèse, you will see the abundances that are actually pretty low as well. And so yeah, my answer here is that it's bad because of the short wavelength coverage. That being said, it's not actually that bad if you see water. It's actually pretty well constrained. And
I said part of the
yep.
probability function. Posterior distribution. Yeah, for sure, you have some detections. Yeah.
Yes. Water. Well, with Hubble, water is pretty much the only thing that you can detect for sure, because of this beautiful water bump that we have at 1.4 microns. It's pretty much, I mean, we're really limited by technology in that case, and water is the only thing that we can really confirm for sure with Hubble because of the short wavelength coverage.
I was wondering, is this if this has been experienced on other targets, this problem with the posterior distribution?
You mean for the carbon, at the limit on the carbon-based molecule? Actually, oh no.
No, I mean this problem of having some limitations from the posterior distribution. Has it been already experienced for some other targets that have been studied with this technique?
Yes. So because and that comes back again with the short wavelength coverage. Pretty much in all of the retrievals that we try to do with Hubble, we have limited posterior constraints because we have so many degeneracies with the atmosphere. We really cannot conclude on anything given the complexity of the atmosphere and given the short wavelength coverage. So besides water, there is really no, on all of the other planets pretty much, and if you even look at the population paper of TRS et al. 2018, where they looked at 30 hot Jupiters, and if you look at the posterior distribution, or even the recent one that was published a couple of months ago, where we looked at 70 transiting planets, and most of the posterior distribution are pretty poorly constrained because of the short wavelength coverage. So this is, again, emphasizing the need of James Webb and Ariel to really be able to have better posterior distribution and better constraint, because we just cannot conclude on anything yet.
Now, on instrumentation, well, I was surprised we did not mention problems with vibrations in your Dr. algorithm.
Yes.
Are you sensitive to vibrations? And if yes, well, if no, no. If yes, how do you handle them? Is there a way to correct for them, or to even take that into account into the algorithm, into the iterations, like, for example, is done with Kalman filtering, for example, to get rid of vibrations? How would you do?
I wish I could answer that question, and I wish I had even faced that problem. It's not even something that even crossed my mind even once, because I don't think I'm sensitive to that. All I can say is that Julien Lozzi has been working on it some time ago, and he found a solution to reduce the amount of vibration. And so when I came in, it was fine. And I actually do not see any vibration. Like the images that I have are pretty well centered. I always need to recenter them, just even for like a fraction of pixel sometimes. But it's not something that has been very present. Actually, not present even at all in my study. Because when I look at the block of 30 seconds with like 20,000 frames, let's say, I run them through a recentering algorithm. Sorry, like just a simple function that recenter all of the data on like just like even like tiny portion of a pixel. And no, it's not something that has been so much problematic. It would be more problematic for pornographic images, actually, because when we have vibration, we kind of bleed out of the coronagraph. And I think actually there is something, an algorithm on Skexeo that corrects that on Sky. And Olivier, correct me if I'm wrong.
Yeah, the vibration, we've always had issues with vibrations. I think every can you hear me?
Yes.
Yeah. And as Nour, so what Nour is mentioning, there are two sources of vibration. They used to be sources of vibration inside our instrument, which is what mostly got fixed before Nour started. And then there are sources of vibration that are due to the telescope with some specific pointing. The telescope has a little bit of vibration that we see, and so those mechanical vibration from the telescope and atmospheric tip tilt. We get all three of those, but I think the major thing that has changed is the instrument vibration is much smaller than it used to be. And I think Dr. Wu is somewhat orthogonal to vibrations because it can't do anything about it, mostly.
Even with a coronagraph?
Well, what it's going to do with a coronagraph is that because Dr. Wu uses fast frame, the frames for which the vibration is throwing a lot of light in the science frame are just going to be excluded from Dr. Wu. Dr. Wu is going to say, I don't like this frame. So it's going to reduce the efficiency, but it's not going to change. It's not going to prevent Dr. Wu from converging.
Okay, thank you very much. Very, very interesting.
Yeah, that's what I meant.
Okay, one last tiny question. Suppose you were, because you mentioned several times that this AO system would not be able to use Dr. Who because they don't have the proper camera.
Yes.
Now, if you were to build an AO system for high contrast imaging from scratch, is there any reason why you would not implement Dr. Who?
No.
Okay, why?
Well, I think the question beyond that is, why do we need a fast focal plane camera? And with we need a fast focal plane camera because this is what allows us to push the contrast, push the photon noise limit and the spectral noise as well. We can run wavefront control algorithms, not only Dr. Who, but also other ones with fast focal plane camera. And the point is really to push down the photon noise limits with even photon counting cameras. And why? Well, I think Dr. Who is just great because it's so transparent to the AO loop. It is really robust. It really does not rely on any model. So it has all of these great characteristics. It only goes well even in simulation. Well, I had issues with the loop divergent, but that was another issue. It does not go bad. Like I tried everything to make it crash. It does not crash. It does not diverge. It's just so robust. And for these reasons, there is, I don't see any reason why if I were to build a high contrast imaging instrument from an instrument activities instrument from scratch, I would definitely have a fast focal plane camera. I would definitely use Dr. Who, but this time with the zones. And I think hopefully soon, like in less than 5 years, who knows, like that would be quite a game changer to be able to correct speckles individually and to use lucky imaging to really kind of bring down the intensity per zone, increase the contrast, and treat really speckles individually, and basically see when the intensity doesn't decrease, to already see on sky like where is the planet, and do planet detection from on-sky observations, and already from telemetry, like instrumentation development. Really, the point is, and there is many ways that we could really optimize Dr. Who and use as well some other algorithms for really seeing already on sky when where is their planet. So yeah, that's what I would do. I would also definitely work on having a better chronograph. Well, I don't know. I was going to say a chronograph that really allows to have a great transmission at short separation, great contrast at short separation. We really want to go closer in. And there is a few things with which we can combine Dr. Who to really move forward with our goal, which is to image more exoplanetary systems and have better observations closer to the star, to see what's happening really in the dynamic closer into the star. Because right now we are mainly observing Jovian planets, and yeah, we want to see smaller planets. And actually, with the paper from Kevin Wagner, there's a Nature paper from him after the NEAR experiment, where they say already with our current telescope, the very large telescopes, we can detect sub-Neptune mass planets with medium-infrared high-contrast imaging data. And so there is already so much that we can do with our current telescopes, and we really need to push forward the instrumentation with chronograph and focal plane wavefront control. There's other things as well, like the self-coherent camera that some people at thèse are working on, which is also a great thing to be able to have better images and EFC as well. And there's just so many things that we can move and push forward for instrumentation development to have better contrast and better data.
Okay, thank you. So there's no trade-off that could lead you not to choose not to implement the algorithm.
Because it's really the only thing that we do is to update the reference, and we need it anyway. And this reference of the wavefront sensor is what drives the whole correction. So
yeah. Yes, but there could be a cost to be able to do that.
Well, we do need the reference to include all of the aberrations, and this is this equation right here. We do want this reference to be the closest from the wavefront error. We really want to minimize that, and I do not. Well, it's there anyway. I do not see any cost at changing it.
Okay. Thank you.
Which makes it great, right? No downside.
Okay, let me finish by a few comments, very short ones. First of all, I loved your manuscript. I would say, like Johanna said, it is clearly your style, and that's very nice to read your style. It doesn't prevent the thesis from being of very high quality, very high scientific quality, but it's not standard, and I really appreciated it. And as far as the presentation is concerned, you were very dynamic, and I think you put a lot of energy, of course, in preparing, as we understood, 4 times or 5 times to rehearse the presentation, but it felt in the result of the presentation today, and it was very enjoyable to follow. Okay. Thank you very much. We're now going to shift to a closed session. So we'll ask everyone to leave the room, please. And we'll be done in less than 30 minutes.